All right, so let's start with elastic potential energy, and this is the second part of chapter 6 lecture. Okay, so by its name, elastic potential energy is basically related to the elastic material. For example, a spring can have elastic potential energy. Okay, so what is the elastic potential energy? So when we have a spring, we can compress it or stretch it. So when you compress or stretch it, the spring basically stores some potential energy, and we call that potential energy as elastic potential energy. And this potential energy can then be do some work. For example, here in this picture, and also I'm going to show a simulation where you will see that so when you compress it, okay, so here in this spring, this is the same spring, okay, so same spring, when you compress it, it becomes something like this. And now there is some elastic potential energy in this spring, okay. So when you release your hand, okay, so the potential energy stored in this spring will work on this ball, okay. And you see that in the last picture number C, you see that the ball gets kinetic energy, okay. So the potential energy here changes to the kinetic energy of this ball, okay. So the potential energy, elastic potential energy can have, elastic material can have only the elastic potential energy. For example, spring is a popular example for understanding the elastic potential energy, okay. So when you compress or stress a spring, that spring basically stores some potential energy. So in this simulation, we can also show the same thing what I show you in this picture, but let's see here in this simulation. Okay, so it's basically same thing, a spring, and here instead of a ball we have some mass, okay. Now so if we push it, okay, so push it means the spring is basically storing some potential energy, and when I release it, you see that that potential energy is converted to the kinetic energy. This spring does some work on the object, okay. Doing some work means the potential energy this spring has, it converted to the kinetic energy of this mass, okay. All right, now let's try to understand what is the mathematical details of elastic potential energy. Okay, let me go back to the slide. Okay, all right, so to understand the mathematical detail of the elastic potential energy, let's consider again this picture, okay. Now, the first picture, first spring is basically the unstretched or undisturbed spring, okay. So it's just a regular spring, no compression, no stretching, okay. So if we have some spring, something like this, okay, this is its natural length, okay, and this natural length, so this is its natural, this is natural length, okay. And this position of this spring we call the equilibrium position, okay. We'll be using this phrase several times, so remember that when the object when the spring is not stressed or compressed, the position of the spring is called the age of this spring is called the equilibrium position, okay. So we'll be using this phrase several times, so remember that this is the equilibrium position, okay. Now if you pull it, okay, so you are pulling this spring in this direction, or pulling means in this direction and compressing means in this direction, okay. So let's try to understand for pulling, and it is basically the same thing for compression, okay. The stretching and compression, compressing, okay. So now we are stretching this spring by applying a force. So you are, this hand is applying a P this force to pull this, okay, to stretch this spring. Okay, now by applying this force, let's say the displacement, let's say we stretch this spring by X amount. Okay, so FP is related to somehow this displacement, okay, the stretching amount. Okay, so how we experimentally found that there is a relation between the applied force and the stretching amount, or here we can also call it displacement. Okay, so from this position, from the equilibrium position to this position, we call the displacement of this spring, and we found that the applied force is proportional to the displacement. Okay, so what it means, it means if applied force is large, the displacement will be also large. Okay, if applied force is small, the displacement will be small. Okay, the same thing for the compression. If you push it hard, you can compress it hard. Okay, if you push it gently, if you compress it gently, the displacement in this direction, this is now the displacement, will be less. If your compress, if your force is less, the displacement will be less. If your force is, if your applied force is high, the displacement will be large. Okay. All right. So with this, we can write this. So because FP is proportional to X, and I want to remove this proportional sign, I want to write an equation. Okay, so we need a proportionality constant. So here we use small k as the proportionality constant, and this k is called the spring constant or the spring stiffness constant. Okay, and it is the property of the spring. So different spring will have different stiffness, spring constant or the spring stiffness constant. Okay, so k is different for different spring, but this is a constant for a particular spring. All right. Now, what happens if you release this force? Okay, so here you are applying a force, Fp. Here you applying, so here also you are applying force Fp. So what happens if you release this force? Okay, so if you release this force, it will try to go back to its original position, equilibrium position. At some point, you will see that when you release this force, at some point it goes back to its equilibrium position. Okay, so how it goes back to equilibrium position? It goes back to its original position because there is some internal force the spring has that helps the spring to go back to its original position. Okay, and that internal force we call the spring force. Okay, the spring force we use subscript S. Okay, S means spring, this S means spring, so Fs means the spring force. We also call this restoring force. Restoring force. Okay, so we call it restoring force because this force helps the spring to restore in its original position. Okay, now restoring force is always opposite to the applied force. If you pull it, then the restoring force will be in this direction, or the spring force will be in this direction. If you compress it, the restoring force will be in this direction. So you see that when you compress it, the spring force or the restoring force is opposite to the compressed force, and here when you stretch it in this direction, the restoring force direction is in this direction. Okay, so this picture tells us that restoring force is always opposite to the applied force. Okay, now what it means mathematically it means the restoring force or the spring force will be equal in magnitude but opposite in direction for the applied force. Okay, so that means restoring forces definition, mathematical definition, is minus kx. Okay, Fs, the spring force or the restoring force, is equal to minus kx. Okay, and it has a special name. We call it Hooke's law, because Hooke's, I think James Hooke's first understand this. So by his name, we call it Hooke's law. Okay. All right. So this is the Hooke's law. Now I want to know what is the work done by this spring force or the external force when we deal with a spring. Okay, so we know that the external force for compressing or stretching is equal to Kx. Okay, K is the spring stiffness constant and X is the displacement. Okay, now the problem here is we cannot use this equation to calculate the work done. Okay, so this is, I mean, we can use this equation when F is constant. Okay, so this is valid only for constant force. Okay, now if we want to use this equation for the for Hooke's law, spring force or the applied force on a spring, we have to use calculus, integration. Okay, but I'm not going to introduce integration here, so we cannot use this equation. Okay, the other method to calculate the work done by work done for the spring force or the applied force in this case is to use the graphical method. Okay, so when the force is not constant, okay, so why it's not constant? Because you see that here it depends on the x. If x is 1 centimeter, then it will be K, like let's say F is 1 centimeter and K is, let's say, 400 Newton per centimeter. Okay, so then it will be 400 Newton. Okay, if F is 2 centimeter, then it will be 800 Newton. So you see that for each displacement, okay, so when you change the displacement, when you change the value of x, the force is changed. Okay, so because of this, we cannot use our regular traditional equation for work done. So and we cannot also use calculus because many of you may not know calculus. So the method we are going to use is the graphical method. I mean, graphical means geometrical method. First we draw a graph, plot a graph, and then we use the geometry to measure or determine the work done. Okay, all right, so how to do that? So to do that, we have to plot a graph, force versus displacement, something like this. Okay, so first let me show this simulation to draw this graph and then come back here. Okay, so let's say we have a spring. Okay, and then so here I have the option to change the spring constant. Let me change the spring constant. Okay, and now here the displacement is equal to 0, so it's undisturbed. Okay, let me stretch it. Okay, let me stretch it, and when we stretch, you see that okay, so let me stretch it. Okay, so you see that when we stretch it, our force versus displacement graph looks like this. Okay, so this is, in this direction we plot force, in this direction we plot displacement. Okay, so this is the displacement, I mean the force versus displacement graph. Okay, now the same graph you basically see in the study guide. Okay, so how to then calculate the work done? So this is the force versus displacement graph. So whenever we have the force versus displacement graph, the work done is basically the area under the graph. So area here is basically this blue part. So this is our graph. Okay, and this, the area under this graph is this blue region, shaded area, blue shaded area. Okay, now how to mathematically determine the the area of this shaded area. So you see, this is a very simple, right? It's basically a triangle, and you know the triangle's area is half base times height. So base is, for this one, base is this and height is this, right? So it will be half, and base is x and height is kx. Okay, because height is force. Here height is basically the force, okay, and applied force. Okay, so applied force is in turn is equal to kx. Okay, so what we get here is the work done by the external force is equal to half kx square. Okay, so this is the method to calculate the work done when we have a spring. Okay, so remember that when we have a spring, it's when we have a force which is not constant, then it's better to first draw a graph, force versus displacement, and then determine the area under the graph. So when we can determine the area under the graph, we are done. Okay, so the area under the force versus displacement graph is basically the work done. Okay, all right. So we will be doing at least one problem. Okay, and there you will see that we can determine the work done by just calculating the area under the graph. Okay. All right. So here I already show it. Now, so here, let me do a little more. So we already see that W by the external force or the pull or push force, whatever, is equal to half kx square. Okay. Now, I want to compare it with, compare this mathematics with the mathematics that we have done in gravitational potential energy. Okay, so remember that in gravitational potential energy, the external force was equal to change in potential energy. Okay, or potential energy 2 minus potential energy 1. Okay, so I want to write in a similar form. Okay, so to do that, I can write this. I can subtract minus 0, right? I mean, we can do it, right? So I can write also something like this, k0 square, right? So, and then when we have something like this, I can write it potential energy at final position equal to potential energy at initial position where x equal to 0. Okay, and you see that it is very similar to this equation, what we see in case of the gravitational potential energy. So when we compare these two, we can say that the elastic potential energy is equal to half kx square. Okay, so the work done, so you first calculate the work done is equal to half kx square. I mean, work done by the external force in stretching or compressing a spring is just half kx square, and this equation is related to this equation. Okay, and then by comparing with it, this equation with the concept of gravitational potential energy, we can show that the elastic potential energy is equal to half kx square. All right. All right. The next thing is we are going to learn is conservative and non-conservative forces. So we are going to now differentiate forces into two categories. Okay, one is the conservative force, and another is the non-conservative force. Okay, so what is the conservative force? Conservative force means the work done by that force depends only on the initial and final position, and not on paths taken between the initial and final position of the object. Okay. And what is the non-conservative force? Non-conservative force is the work done by that force depends on the path taken between the initial and final position of the object. Okay, so what I mean here, for conservative force, we basically need to know the initial position and the final position. But for the non-conservative force, when we calculate the work done, then we need to know the path in which it is moving, in which the object is moving. Okay, so for example, when we determine the gravity, okay, gravitational potential energy, or the work done by the gravity, you know that we just need to know the initial position and the final position. We don't need to know in which direction we move the object from initial position to the final position. Okay, so the gravitational potential energy depends on the height, okay, not the position, not the path, how it moves. Okay, so that's why the gravitational force is a conservative force. Okay, and for conservative force, we can determine the potential energy. For each conservative force, we can determine the corresponding potential energy. And we already see that for gravitational force, we calculate the gravitational potential energy. I mean, we derive an equation for the gravitational potential energy, and also for the spring force. Okay, we derived an elastic potential energy. So gravitational force and the elastic force are the conservative force, and many other forces, for example, the friction, air resistance, tension, rocket propulsion, push or pull, all are the non-conservative force. Because for these forces, when you want to measure or determine the work done, it basically depends on the path. For example, if you push this box in this direction, the work done will be different if you push this box in this direction. Okay, same thing will be happen for the work done by the frictional force. The work done by the frictional force will be different if you move in this direction than in this direction. Okay, so the friction, air resistance, tension, push, pull, or rocket propulsion, all are the non-conservative force. And for non-conservative force, we cannot determine a potential energy. On the other hand, the gravitational force, elastic force, and electric force, we are not going to consider it in this course, are all conservative force. For all conservative force, we can determine a potential energy. Okay, so gravitational force and elastic force, if you want to work done by them, we just need to know what is the initial position and what is the final position. Okay, all right. Now, next thing we are going to understand is the conservation of mechanical energy, and then conservation of energy and power. Okay, so I'm not going to derive the conservation of mechanical energy here. I derived. Those who are interested, please go through it. If you have question, let me know. And the same thing for conservation of energy. Okay, so conservation, what conservation means, first we need to understand. Conservation means constant. Okay, so no matter where you I mean, if we have a system, and if it goes through some change in position, let's say, okay, no matter where it is, the mechanical energy is always the same. And remember, the mechanical energy is equal to the kinetic energy plus the potential energy, right? So the mechanical conservation of mechanical energy tells us that the mechanical energy is constant always. Okay, now this is valid only when there is no work done by non-conservative force. Okay, so if we neglect somehow the work done by the non-conservative force, okay, then the mechanical energy is constant. Okay, but if we have some contribution from non-conservative force, okay, then this is not valid. Okay, so remember that conservation of mechanical energy is only valid when WNC is equal to 0. Okay, so mostly when there is no work done by the friction. In this chapter, basically we are by non-conservative force, we will mean the friction or the air resistance, although push pull all are the non-conservative force. But in this chapter we are not going to discuss the difficult thing. So the only two forces we are going to consider for non-conservative force are the friction and the air resistance. Okay, so what it means when there is no work done by the friction or air resistance, then the kinetic energy plus the potential energy at any position is equal to kinetic energy and the potential energy, I mean sum of the kinetic energy and potential energy at any other position. Okay, all right, so here I already derived it. I'm not going to show it how I derived, but I'm going to show a simulation. Okay, all right. All right, so here we have, let me take this complicated track. Okay, all right, now let me put this here. Okay, so at this point, okay, let me push this person, put this person at the top height. Okay, so here you see that if you look at the graph here on the left hand side, the energy graph. Okay, so here you see that all the energy currently this person has is the potential energy, right? You see that, and it makes sense because the potential energy is equal to mgy, right? This person has mass, we have the gravitational acceleration, and the height is about 5 meters. Okay, so because of that, all the energy this person currently has is the potential energy. Okay, and you see that the speed is equal to 0. Okay, now here we neglect the thermal energy. Thermal energy is basically due to the friction. So here let's see, okay, so let me check that whether I neglect the friction. Yeah, so there is no friction basically. Okay, so here there is no friction, so that means we are fine. Okay, so we neglect the friction, although in real life there is friction between the board and the track, right? But if we neglect the friction, the total mechanical energy is constant, no matter where this boy is. The total energy is always constant. So you will see when this boy is moving, okay, from one side to another side, you will see that there is no change in this total energy. There will be change in the kinetic energy and potential energy. Okay, but the sum of the kinetic and potential energy is always equal. So that is the conservation of mechanical energy, and it is valid only when there is no work done by the friction. I mean, friction means here friction means the non-conservative force. Okay, so if there is no work done by the non-conservative force, the total mechanical energy is constant, and mechanical energy is sum of the kinetic and the potential energy. So kinetic energy and potential energy may change, but their sum is always constant. Okay, so here you see that. So now at the highest point, this person has only kinetic energy. Okay, so you see that now I mean at the highest point it has only potential energy. So you see the only potential energy. Okay, And then if you look at this energy graph, you will see that there is no change in the total energy, but there is a change between the kinetic and the potential energy. So let me go slowly and see that. So you see that now at this point, when the boy is at 4 meter, it has some potential energy, it has some kinetic energy, but the kinetic energy is increasing, potential energy is decreasing. Okay, so you see that now kinetic energy is decreasing, increasing, potential energy is decreasing, but there is no change in the total energy. Okay, so when at the ground, so you see that there is change in kinetic and potential energy. And the thing I want to show is here. So here at this point, you see that most of the energy is kinetic energy. There is no potential energy. And it makes sense because when the h equal to 0, the height equal to 0, there is no potential energy, right? Because mgy, because the potential energy is equal to mgy. Okay, so if we neglect the friction or air resistance, or in general, if you neglect the work done by the non-conservative force, then the mechanical energy at any point is constant. Okay, so we'll be doing many problem using this concept. Okay, now let me go back and then talk about the conservation of energy. The next topic we are going to learn is the conservation of energy. Okay, so this is the conservation of mechanical energy. Okay, so conservation of mechanical energy means when there is no work done by non-conservative force. But what happens if there is a contribution from non-conservative force? So if there is a contribution from non-conservative force, then the equation becomes this. Okay, the equation becomes this. It's very similar to the conservation. Conservation of mechanical energy, but now we have to add work done by non-conservative force with the mechanical energy of the position 1. Okay, so the conservation of mechanical energy was this, right? Now, when there is a contribution from non-conservative force, we have to add it to the position 1, the initial position. So remember that conservation of energy, when there is a contribution from non-conservative force, it should be added to the initial position. It should be added to the mechanical energy of the initial position. Okay, so here you see I add WNC with this one, KE1 and PE1. Okay, don't do it here. Okay, all right, so this is the conservation of energy. Now let's say if the non-conservative force is the friction force. Okay, so now let's try to calculate WNC. So WNC for the friction force will be this, right? And you know that the friction force and displacement is always opposite to each other. So the cosine theta is cosine 180 degree. Okay, so it will be minus friction force D. Okay, so the equation now becomes something like this: KE2 plus PE2 equal to KE1 plus PE1 minus this. Okay, so if I ask you to calculate WNC, then you just use this equation. Okay, when if I ask you to calculate the friction force, then you have to use this equation. Okay, all right. So the conservation of mechanical energy tells us this, but in word it means that energy cannot be created or be destroyed. Energy can only be transformed from one place to another place or one form to another form. So this is the conservation of energy. So if I want to express this in word, then the conservation of energy states that we cannot create energy or destroy energy. We can convert energy from one form to another form, or we can transform energy from one place to another place. Okay. All right. The last thing is the power. Okay, so power is the rate at which the work is done or energy is transformed. Okay, and the mathematical definition of power is W over T. Okay, so W is the work done, T is the time or the change in energy over time. Okay, now here the change in energy could be just change in potential energy, or it could be just change in kinetic energy, okay, or it could be both. Okay, so change in energy means the total energy change. Okay, in some problem it is just the change in potential energy, in some problem you will see it is just the kinetic energy, in some problem you will see it's the combination of both. Okay, so for example, when you talk I'm going to talk about this. So here it is just the change in potential energy. Okay, all right, so similar to the work and energy, it is also a scalar quantity, and from this equation you can show that the unit, the standard international unit, is joule for work done or the energy, and second for the time, so it's joule per second. Okay, so powers standard international unit is joule per second, and it has some special name, we call it watts. Okay, and to avoid the confusion between W and the symbol for the watt, I normally do not use this symbol. I would not use. Okay, so if I were if we need to express watts, I would write watts, the full word watts. Okay, so that's why we can avoid the confusion between the same symbol for work done and watts. Okay, so remember that, although we can use this for the standard international unit, but don't use that. Okay, to avoid the confusion. All right, so 1 watt means 1 joule per second. Okay, now to understand this, let's consider this picture here. So in this picture we see that a person is walking from the bottom to the top. Okay, so this person is the first person is slowly walking from the bottom to the top, and this person is walking quickly. Okay, let's say the mass of this both person are the same. Let's say both person has mass equal to m. Okay, now at the bottom, okay, here the potential energy is 0. Right, we can say that the height is equal to 0 for both person, so the potential energy here is equal to 0. At the top, the potential energy is mgy for both person, because both person have the same mass. Okay, so the change in potential energy here is in final potential energy minus initial potential energy. So the final potential energy is mgy, initial is 0, so the change in potential energy is just mgy. Okay, now what is the power they used? So the power they used is equal to mgy by T, right, average power. Now this person, the first person, is walking slowly, that means T is more for the first person, and the second person is walking fast, so for the second person T is low. Okay, now when you plug this time in this equation, you see that the first person is using less power, right, because more T in the denominator means less power. Okay, so when when someone is walking slowly, that means he's using less power. When a person is walking quickly, that means when the time in the denominator is small, that means the power is more. So in this problem, you can see that the second person is using more power to go from the to walk from the bottom to the top. Okay, all right. The last thing here I am going to talk is another form of power. Okay, so now you know that work done can be written as this: W equal to FD cosine theta. Okay, for simplicity, let's say the direction of the force and displacement are the same, so then it will be just FD. Okay, now the power or average power is W over T, and that can be written as FD over T, right? Now it can also be written as distance or displacement over time, right? And if you remember from the chapter 2, the displacement over time is the velocity. So power can also be written as the product of force and velocity. Okay, so in one problem we are going to use this equation: the power is equal to force times velocity. Okay, so for example, here this train is moving in this direction, so the force the engine is providing is in this direction, and the velocity is in this direction, so both are in the same. So for this train engine, we can calculate its power by using this equation. All right, so that's it for today, and in the next lecture I'm going to solve some problem from this chapter.